All right, so we've talked about 2 points where you have concurrent lines. Remember what we talked about yesterday, concurrent lines? What does that mean to be concurrent lines? All the lines intersect at the same point, okay? So we talked about that. What were the first two words that we did before these two? Circumcenter and orthocenter. How'd you find the circumcenter? Not parallel bisectors, perpendicular bisectors. How'd you find the orthocenter? The altitude, okay? So what we're going to do today is talk about the incenter. So if I had an angle, oops, got to do this. I've been using this program for so many years and I still forget. Yes, sir. Don't go to the bathroom. No. All right, put it up there on that pile. Thank you. All right, what if I had an angle right here and I asked you to bisect the angle?
Cut it in half.
Exactly right.
2 even parts.
Okay, yeah, 2 equal angles. Very good. 2 even parts. That's good. Bisect the angle. All right, so what I would do now, just on this is just a writing program. I can't really like measure. I don't know, maybe there is a way to do it, but I'm just going to eyeball it, okay? So do you think that bisected the angle? No. Do you think that bisected the angle? No. Tell me when. I'd say about right there. That's pretty close. Again, we're just eyeballing it, okay? But we are going to use GeoGebra in a minute, and GeoGebra can exactly bisect an angle. This is Incenter, okay? So what we need to know about the incenter is we need to know that we bisect the angle, which means that this angle and this angle right here will be what to each other? Will be equal to each other, okay? So these two angles will be equal if this bisected the angle. Everybody got me on that? Okay, so what we're going to do is we are going to go to GeoGebra right there. Oops, there it is. All right, and we are going to bisect an angle. So let's just do an angle right now. I did not practice this. I'll just do this. There's that, and there's that. I think it'll do it. And I could find that angle. I could, right there, measure the angle. So I can click on this, I can click on this, and there's your angle right there. EJ, are you listening to me? Okay, all I hear is you talking. And I didn't even have to look. Okay, there we go. Let's say we'll make that a nice even angle, 70 degrees. Okay, if I wanted to bisect it, I don't know, let's just for fun eyeball it and tell me when you think it's bisected. Right there? Up a little bit? Down a little bit? Down? I would say up a little bit. That's pretty close though, don't you? Wouldn't you agree? All right. Just for fun, well, not just for fun because this is what we're trying to do today. What I want to do is now actually bisect it. So that was eyeballing it, right? Just kind of guessing. Let's see how close we were. This has got a thing called angle bisector. And if I click on this and I click on this, boom, there it is. So we were off a little bit, weren't we? All right, so that's why it's good not to eyeball it. But what I will do is this. I'll put it right on there. Well, let's see if it is. How can we check to see if it is? Right, measure the angle. So let's do this one and this one. There it is. I know it's hard. Oops, that's the 70. There we go. There it is. It's 35. So were they right? Yeah, they bisected it. Okay, we were off a little bit. It's kind of close, but you can see what it means to bisect something. All right? We good with that?
Yeah.
All right. So now, what do you think we're going to do with all this stuff? Tell you what, let's just clear this whole thing. How did I do that yesterday? Clear all. There we go. How about that? Okay. So now, what do you think we're going to do now? A triangle, right? And then what do you think we are going to find? Okay, we're going to find the incenter. And how do you find the incenter? Bisect the angles. Very good. We bisect the angles. So here we go. Let's bisect the angles. So where was that? Right there. Angle bisector. Do you see it? So now I click on this one and I click on this one and boom, it bisected the angle. We're going to get rid of all those lines. Not really sure why they put this line right here. I've always wondered. There's got to be some reason. Maybe just to show it in reference to a 90-degree angle. We'll get rid of those in a second, all right? But what I want to do is bisect all three angles. Now, take a wild guess. Hopefully it's not that wild of a guess because we've done it twice already before. But what do you think is going to happen to those angle bisectors? Intersect all at the same point, right? Okay, so let's do that. So let's do this one and this one. All right, so here's where those two intersect, right? I mean, really, any two lines intersect each other unless they're parallel. Would you agree? All right, if they're in the same plane. All right, so watch this. Bam. Oh, there we go. Look at that. They intersect right there. That's pretty cool, isn't it? Do they form something cool? Yeah, kind of looks cool. All right. Yep, you got a whole bunch of stuff in here, okay? But what I'm concerned about is that point right there. And what do we say we're going to call that point? The incenter. It's the incenter, okay? Let's do this. Let's get rid of all this mess. Boom, boom, boom. Just to make it a little easier for us to see. That looks a little cleaner, a little nicer. Do you remember what we did with that circle and that circumcenter? That circle circumscribed, it went around the outside of the triangle, didn't it? Well, this is not a circumcenter, it's a what? It's an incenter. Where do you think the circle is going to be here?
Inside.
That's right. Okay, so if I can do this, I should have practiced this. Remember what I used last time? Was it circle with a center? Then if I click on this, oh, there we go. Yeah, check it out. Look. It's perfect right there on the circle. Do you see how it touches here, here, and here? All right, so that's kind of cool, isn't it? What? You can ask. Go ahead.
It might sound dumb, but like, why is the circle on the inside?
Because it's an in-center. Okay. You weren't supposed to be till 2:55. That's all right. It's fine. All right, but look at this. Look. This is not a circumcenter, is it? Because, look, it might go through two of those points, but everybody looking? Seems like lost everybody's attention just because somebody's leaving. So it's not a circumcenter because that circle would touch all three vertices on the outside of the triangle, wouldn't it? Okay, but if I bring it in, look at that. It's right. So it hits the circle, or the triangle. The circle hits the triangle at all 3 points. Do you see that? So that's an incenter. So that's what we can do with that. So that's kind of interesting. Let's get rid of that. Here's what I really want you to see. There's something special about that incenter. The circle is inscribed in. It's not circumscribed. It's inscribed. Why is it inscribed? Because the circle is inside the triangle. Make sense? Circumscribed means outside. All right. So that's the difference between the two. But there's also something really interesting about this. The incenter is here's that word equidistant again. I think we got that cleared up from the other day, I hope. The incenter is equidistant, not from the angles or the vertices. That was the circumcenter. Remember that? Okay, it was equidistant from the vertices. This one is equidistant to the sides of the triangle. What do I mean by the distance from this point to this side? Here, I'll just do a segment here. Is that the distance from the incenter to that side? Is that the distance? Is that the distance? What would the distance be? If I asked you to give me the distance between this incenter and this side AC, where would you draw it? At the midpoint? Midpoint's about right there-ish. It's not at the midpoint. It's going to be, it might be close because of the way the triangle is drawn, but it's actually perpendicular. Okay? The altitude, right? We talked about the altitude before. The altitude is the distance between a point and a side. All right? For instance, let's say a plane is flying over. Okay, normally I would draw, well, let's just do it right here. Oops. There we go. Let's talk about altitude. We've talked about it before, but I never did this. Let's say this is the ground. All right, that's the ground, and here's your airplane. It's my cool airplane. I'm the world's worst artist. I can't even draw a triangle. All right, there's an airplane. There's the cockpit right there, and here's all the exhaust, okay? That's your airplane, all right? So you're in an airplane, and the pilot gets on there, and a lot of times, anybody flown commercial before, okay? The pilot will get on there and telling you where you're going, how long it's going to take, but it'll also tell you your altitude. When he says the altitude, what is he talking about? Is he talking about the distance from here to there?
No.
Is he talking about the distance from here to here? No. What distance is he describing? Straight down. Okay? But what word do we use in geometry instead of straight down? Perpendicular. Exactly right. So that right there, let's click off of that. Come on, there you go. Watch. So this is the distance from this point to this line, thinking the earth is the line, okay? Everybody with me on that?
Yeah.
So that's the distance. It's what? It's perpendicular. Let's go back to GeoGebra. All right. So let's get rid of that incenter thing. So what am I going to have to draw from that incenter to this line? What kind of a perpendicular? Okay, no, not bisector. Okay, it doesn't necessarily hit the midpoint. It just has to be perpendicular to that line. All right. So what I'm going to do is click on here, click here, and there's your perpendicular. That's a 90-degree angle right there. Okay? Now watch. Remember what I said about the incenter. It's equidistant. It's the same distance from that incenter to every side of the triangle. So what's the distance from this incenter to this side right here, BC? It would be from here to where? Perpendicular to here. Okay, perpendicular. And they draw this whole big old line that keeps on going forever. We'll make it a little smaller so we'll see it a little bit better. So watch, incenter to here, and there it is right there. So what I'm going to do, so we can get rid of those lines, I'm going to draw from here to there. See that distance from the incenter to point D? And this incenter to that point E, and from this incenter to point F. I don't think I got it right on there. I want to make sure I get it right. I think that's on there, okay? All right, let's get rid of some of those other things I just drew. This line, this line, this line. Okay. They don't look the same? Well, let's see if they are. How can I do that? Distance or length? 3.3, 3.3, 3.3. Are they the same? It doesn't make any sense?
No, look, if you're looking at this picture, doesn't the bottom one look like if you
This one right here?
Yes, that one looks like if you longer.
All right, I'll tell you what. I'm going to put the mic down for a sec. If you don't believe, whoops. There you go. If you don't believe GeoGebra, you believe a meter stick? Okay. So,
No, I understand that is what it is. I'm just saying it doesn't look like it.
well, that's what I'm showing you. I know that's what you're saying because that's what I'm going to prove to you. So watch. From here to here, that's about 17. You see that 7 right there? About 17 centimeters. Okay. Did you see it? The 17? You can't see? That right there. See that 7? Right there, 7. Right there. That's 17. What's this one? there it's at 7. 17. And what's this one? 17 right there. So it may not look like it to your eyes, but we measured it. Okay, we had GeoGebra measure it, and if you don't believe GeoGebra, we actually took a meter stick and we measured it, and you should believe it now after seeing the meter stick. Wouldn't you agree? All right, so they are equal to each other. Now, what's cool about this, well, let's click off of there, is watch. It doesn't matter how I draw this thing. And also, look at the incenter. It doesn't matter if I have a obtuse triangle or an acute triangle or a right triangle. Where is the incenter always going to be located? The incenter. Where is it going to be located? Inside the what? The triangle. Everybody see that? It never went outside the triangle. Do you remember circumcenter and orthocenter? Depending on how you drew the triangle, sometimes it went outside the triangle. Right? Would you agree? But on the incenter, it always stays where? Inside the triangle. In center. Got it? Okay, that's kind of cool, don't you think? And look at the distances between the sides. Do they ever change? No. All three of those distances are, give me a word, starts with an E. Equidistant. Right, it's equidistant. So that's kind of cool. How did we find the incenter to begin with? We bisected the angles, exactly right, okay? So how did we find that incenter right there? We bisected the angles. Now I got rid of that because that would be a huge mess if I had all those lines flying all over the place, wouldn't you agree? All right, but how did I find this? I bisected this angle, this one, and they all met, bam, right there. Now, what's special about the incenter? Well, a couple things, but the thing I really want you to understand, and the things you're going to have to know for homeworks and quizzes and tests, is that it's the same distance to all three sides of that triangle. Does that make sense? Yeah. Okay, so that's kind of cool, isn't it? All these things, how it all comes together is kind of neat. All right. I think we're done with incenter. Everybody good with that? All right, let's go to the next one. And we talked about this a little bit yesterday. If you weren't here yesterday for the choir thing, I forgot to put the video up last night, but I did put it on this morning, so it is on there. But that's okay because you don't have to be here yesterday to know what we're going to do right now. Let me clear this. Don't save it, and let's do another one. Let's talk about this again. So watch, this is just a segment, okay? It's not a triangle, it's just a segment. But what if, no, let's not do that. Let's go right to the triangle. All right, so let's just draw any old triangle, right? Nothing special about it. There we go. Okay, so what we're going to do is introduce another name, and I didn't write these names on here, but I think you'll be all right. Yeah, okay, I was just checking to make sure this was showing. What we're going to do now, well, let's put this word up here. I don't know if we've used this word before. And it's called median. Have we used that before? Yeah. Okay, good. So if you're driving down the road, especially on a highway, you got a bunch of lanes going this way. If you're on 95, right? Bunch of lanes going this way, bunch of lanes going this way. There's usually like this big grassy area in between. Would you agree? You've seen that before? What do they call that grassy area? They call it the median, right? They call it the median. Sometimes it's concrete, sometimes it's grass, sometimes there's really nothing. There's maybe just a line in between or something like that. But the median is the thing that's in the middle, all right? So a median in geometry is when we go from an angle to, where do you think? The midpoint, right? The middle, right? Median is the middle, right? So when I draw a line from a vertex to the midpoint, that would be considered a median. So what do we have to do before we draw the line? We don't want to eyeball it. We just saw a few minutes ago, just eyeballing doesn't really work that way, does it? Doesn't work that well, I should say. So what am I going to have to do over here. Find the what? Find the midpoint. There it is right there. Midpoint. Watch. I click on there. There's a midpoint. Click on here. Midpoint. Click on here. Midpoint. So now what I'm going to do is I am going to connect from a vertex to a midpoint. Everybody see it? From a vertex to a midpoint. And one more, from this vertex to this midpoint. And lo and behold, look what they do. They all intersect at one point. So they're concurrent lines. You getting all this vocab? Right? A lot of new words in geometry, isn't there? All right, so those are concurrent lines and they all meet at that point. Let's put a point here where they intersect, right there. And let's call this, what do you think we're going to call this one? The centroid, that's right. So this is called the centroid. How did we find the centroid? We drew the median of all three sides of the triangle, okay? So the median. Everybody got that? How did you find the centroid? We took the median of all three, I guess you could say angles or vertices or sides. I'm not sure how you would say it. But anyway, you go from a vertex to the midpoint of the opposite side. Okay? So I go from a vertex to the midpoint of the opposite side. That's called the median. So that whole line from B to D, that's a median. From A to F, that's a median. From C to E, that's a median. Okay? And if you do that, they all intersect each other at the same point called the what? The centroid. All right? Now, there's something special about that centroid. I'm going to keep those lines there because these, well, actually what I'm going to do is this. I don't think I'm going to do it to all three of them. I'll just do it to one of them. I'm going to make a little segment from E to the centroid, and then I'm going to make another segment from C to the centroid, and then I'm going to get rid of, if I remember which one it is, is it that one? Nope, not that one. Is it this one? Nope. It's this one. Yeah, there we go. That's the one. So now I got two segments, okay? Instead of that one big long one, I got two little segments right here. What I'm going to do is I'm going to, well, let me ask you. There is a relationship, I'll tell you right now, okay, between the centroid to point E and from the centroid to point C. Now, do they look like they're equal to each other? Yeah, they definitely don't look equal. That little E to centroid and centroid to C, do they look the same? No. This one looks quite a bit bigger, doesn't it? In fact, this one right here, the one that goes to the vertex, it's double the one that goes to the midpoint. Did you hear me on that? Okay, so from the vertex to the centroid is double from the centroid to the median. So if this right here was 5, I'm just making up a number, okay? From E to the centroid was 5. What is it from the centroid to C? It's 10. And then what is it from E to C? 15. You got that? Yes. It's 2/3. I know. We're going to talk about that in a second. All right, but I'm going to do it the easiest way first, okay? So what I'm going to do now is I'm going to put the numbers in here and let's just see if that's really true, distance or length. That's why I made them segments. So 5.3, so what do you think this is going to be? And there it is, right there. Isn't that cool? And it doesn't matter. I can move this thing around and watch what happens. Now they put 8.5. This is 4.2. This should be 8 point what? 4. Why do you think they put 0.5? Because the rounding part, right? Okay, because of the rounding. But if I move it around just a little bit, there's the 8.4. Okay, so it's just because of the rounding up or down. All right, but you can see, move it all around. Look, there you go. That's 10. That's 5. What is EC? It's 15. All right. So here's what Cameron brought up. The book talks about this 2/3 thing. It's the last thing that I talk about because I want you to understand that one segment is twice as big as the other one. Or one segment is half, right, of the other one. Would you agree? 5 is half of 10. Agreed? 10 is twice as big as 5. But what is 5 to the whole length? What fraction of the whole length is that segment 5 right there? It's 5 out of what? No, it's 5 out of 15. The whole thing is 15. Reduce 5 over 15. It's 1/3. So from the centroid to the midpoint is 1/3 of the whole entire thing. You hear me? It's 1/3 of the whole thing from east to EC. But it's half of this segment right here. Are you getting this straight? Yeah. Okay. So that's what they mean by the 2/3. Because what's 10? 10 over 15 is what? 2/3. So the 10 is 2/3. The 5 is 1/3 of the whole thing. Okay? But you could also look at it as the 10 is what? Twice as big as the shorter one. And the shorter one is half of the longer one. All right? So that's what's special about that. And it works for the other ones as well. Like from A to the centroid and from the centroid to F, it's the same exact thing. There'll be different numbers, right? But this is still, this little one right here is half of this one, right? This little one right here, from D to the centroid, that's half of this one right here. Okay, so it works for all three of those. That's pretty good timing because that's all I had. You do have a homework assignment, so don't run out. You're not going to miss out on that. So it's only 7 problems, 1 through 7. So it's 5-2A, and it's 1 through 7. That's it. I don't know. Just look at section 5-2. All right, that's your homework. Have that done.